One of the real advantages of the electric potential is that it's a scalar quantity. And what this means is that you can calculate electric potential much easier than you can calculate an electric field. So, for instance, the electric potential from a system of charges would just be equal to the potential from each charge. You literally just sum them up. So let's say that you had a system of point charges, K, Q, I over Ri, and they're not vectors. So you don't have to even worry about summing them as vectors. You just sum them individually. Same thing with the electric potential energy. If you want to you can sum up the potential and then multiply it by the potential energy of a test charge or whatever. That gives you the potential energy of everything. One of the key results from this, I want to go ahead and calculate this because this is called a charge dipole. All right, so let's pretend like we have a plus and a minus charge along the z-axis. And we want to calculate the electric potential from this system of charges. All right, there's one here and there's one here. So this we're calling R plus, this is R minus. Okay, notice I don't have to worry about vectors here. And the R, the point we're calculating the potential at, is at distance R from the origin. We're going to let this angle here be theta. All right, so what the potential formulation says is that if I want the potential at point P, I just have to calculate the potential from the plus charge plus the potential from the minus charge, and that's going to be KQ over R plus KQ over R minus. Now the rest of this is just kind of the algebra that I have to do. Whoops, except I missed one detail. This is a plus Q, this is a minus Q, so it's actually KQ minus KQ over R minus, because the Q plus is plus Q, the Q minus is minus Q, whatever. All right, so let's see, how do I do this? Well, my point P is at location X. That is the same for both. The X location is the same for both these charges. What's different is the location of Z, okay? So the point P is at location Z, but the distance, I could do it like this. R plus, if I want to just use vectors, R plus is R, X hat plus, and then it would be Z. And what I'm going to do is I'm going to use this distance between the two charges as D. And you'll see why I do that in just a minute. So this one is at Z minus D over 2. Okay? And then in the Z hat direction. And R minus will be X hat plus, and then that distance is going to be Z plus D over 2 in the Z hat direction. Now, what I'm using here, R plus, that's here in the denominator, that's just the magnitude of vector R plus. So if I want that magnitude, well, my magnitude of the vector is really easy. It's the square root of one component squared plus the second component squared, and that's it. Okay, R minus, same thing. It's the magnitude of R minus vector, which is x squared plus, and then this one would be Z plus D over 2 squared. Easy, simple stuff. So it's going to help things a little bit for me to write this in terms of this value R that I've got here. And so what I can note from here, I've got this triangle like this. This is my X, this is my Z, this is R, this is theta. So the way that I've formulated this by taking theta from the y-axis, you can see X is equal to R sine theta, and Z is equal to R cosine theta. So I can express these two things like this. R plus is equal to r squared sine squared theta plus, and then in place of z, r cosine theta minus d over 2 squared. And then r minus is equal to the same r squared sine squared theta plus r cosine theta plus d over 2 squared. All right, and so now I'm going to take the r out of there because let me expand it a little bit. Plus, and what I've got here is r squared cosine squared theta plus d squared over 4, okay, minus, there would be a 2, I'm just doing 2 r cosine theta d over 2. Okay, same thing here. R minus is equal to r squared, r, taking the r out. No, I'm not. I didn't do that yet. R squared sine squared theta plus r squared cosine squared theta plus d squared over 4, and then plus 2 r cosine theta d over 2. All of that. So simplify. R plus is equal to, and what I've got here is r squared sine squared theta plus cosine squared theta. So that's just r squared because sine squared plus cosine squared is 1. Minus, notice the 2 cancels out, so I've got r d cosine theta, and then plus d squared over 4. R minus is equal to the square root of the same r squared plus r d cosine theta plus d squared over 4. Okay, and now we make a stipulation that r is much bigger than d. Okay, and so what that means is that the field point that I'm evaluating this thing is way far away from this charge dipole. All right, and that will allow me to do this. I'm going to take the r's out, and I have 1 squared, 1, which is true, 1 minus d over r cosine theta plus, and I'm going to write this as d over r squared, and I can write that times 1/4, but you'll see what I'm getting at here in just a second. Same for r minus. R minus is equal to r 1 minus, or plus rather, d over r cosine theta plus d squared over r squared, or d over r squared rather. Write it like that. So if d over r, if r is much greater than d, then that means that d over r is actually much less than 1. And that means that d over r squared is way less than d over r. And so these terms can effectively be left out. R plus is then approximately equal to r times, let me write it like this, 1 minus d over r cosine theta to the 1/2, and r minus is approximately equal to r 1 plus d over r cosine theta to the 1/2. Okay, so now I can go back to what we call the binomial approximation, and that tells me that 1 over the 1, and I'll write it like this, minus or plus alpha to the 1/2 is approximately equal to 1 plus or minus alpha over 2, which means that 1 over r plus is approximately equal to 1 over r times 1 plus, I'd have to put the plus sign in there, d over 2r cosine theta. And same thing, 1 over r minus is approximately equal to 1 over r times 1 plus 1/2, or minus rather, d over r cosine theta. No square root. So my VP then is represented as KQ, remember it's KQ times 1 over r plus minus 1 over r minus, right? Yep. And then that would be KQ over r times 1 plus d over 2r cosine theta minus 1 minus 1 over 2dr cosine theta. And so equals KQ over r. The 1 is going to cancel out, and I get plus d over 2r plus d over 2r cosine theta, which is d over r cosine theta. And so this ends up being KQD over r squared cosine theta. That's the potential at point P. All right. And so I can better represent this by what's called the electric dipole moment, P. And it's represented like this, Q d vector. The d vector is this distance right here, this distance. This is d vector. Okay? It's the distance from the negative to the positive charge. And so when I write d dot r like that, for this example here, what that would give me is basically z hat dot r hat, right? Z hat, d z hat dot r hat, which is d cosine theta. And that's where this term comes from. So the dipole, the potential from a dipole moment, a charged dipole, is equal to, at point P, K P dot r hat over r squared. And that's a nice little way to express the potential from a charged dipole. Okay? And it's a result that we'll come back to several times. So back to the system of charges, what if you don't have individual point charges? So point charges, it's the sum of KQI over RI. But if you have a continuous charge distribution, what if it's not individual point charges? Well, then it's pretty simple. You just integrate the differential charge over the location of each differential charge. And that's how you calculate the potential from continuous charges. Three classic examples. If we have a line charge, lambda equals, I'm sorry, let me do it this way. Lambda, line charge lambda, where dq would be lambda dl. Then The potential is just K lambda dl over r. Lambda may be uniform, in which case you can bring it out of the integral, or it may not be. Surface charge, sigma, which would be dq is sigma dA, and so then you're just integrating over the area, same thing, and you can have a volume charge density too. Rho, which would make dq equal rho dv, and leads to the potential expression being v rho d. Now this v is different than this v. That can get a little confusing. There's some examples that you can follow in section 7.3. I think it's a good plan to do that. I'm going to leave those for you to follow. Now, here, the thing is, I said electric potential is a lot easier than calculating electric field, and that's right. But what if you really need to calculate electric field? Well, it turns out that that's not too difficult to do. Remember, if we have a uniform field, then we found that the electric field is just equal to minus the potential energy per distance, right? And so let's break that down into infinitesimal. Then what we can say is that the electric field in the direction of the displacement, that component of it, is equal to minus dv ds. So if these were individual components, we would say the electric field in the x direction would be minus dv dx, the electric field in the y direction would be minus dv dy, the electric field in the z direction would be minus dv dz, and all of that's completely correct. So but the thing about that is it's possible that to be more general, the electric field, the electric potential V could be a function of x, y, and z. This would be true for a uniform field. They would be total derivatives. But what if V was a function of all of those variables? Well, then you'd have to do it like this. You'd have to take the partial derivative of v with respect to x. For y, the partial derivative of v with respect to y, and for z, the partial derivative of v with respect to z. No big deal. But now look, I've got the x, y, and z components of this. And so I could just say that the electric field vector is equal to dv dx I hat plus minus dv dy j hat plus minus dv dz k hat. And so this, in fact, suggests the definition of the vector operator del, which is this operator, partial with respect to x I hat, well, I guess plus the partial with respect to y j hat plus the partial with respect to z k hat. And then I could apply that operator to the voltage, for instance, and I could write E is equal to the negative gradient, this is called the gradient operator, of the potential. E is equal to minus grad V. Sometimes you have symmetry other than rectangular or Cartesian coordinates, in which case you just replace this operator with the respective coordinate system. So in cylindrical coordinates, the del operator looks like this. R hat partial with respect to r, plus phi hat 1 over r, partial with respect to phi, plus z hat, partial with respect to z. And in spherical, we're just giving these right now. It's interesting to find out where these coefficients come from, but for now, we'll just kind of trust that this is where they come from. There's a theta direction, and 1 over r partial with respect to theta kind of fills the role of phi in cylindrical. And then there's a phi in spherical that looks like this: 1 over r sine theta partial with respect to phi. And so you can do any coordinate system like that. They've got some great examples. The easiest one is field of a point charge. Since there's spherical symmetry there, you want to use the del operator in the function of spherical that we just wrote. But it turns out to be really easy then, taking the potential of, well, let's just do it, point charge. So we know the potential from a point charge is V equals kq over r, scalar function. Can I calculate the E field from that? Sorry, my handwriting, you know, it is what it is. Sure, E is equal to minus grad V. I'm putting the vector, yeah, that's good. Okay, so minus, here's what the operator is. R hat partial with respect to r, plus theta hat 1 over r partial with respect to theta, plus phi hat 1 over r sine theta partial with respect to phi, and times all of that applied to v. Notice that the only dependence of v is kq over r. So there is no theta dependence there. There's no phi dependence there. And what that means is that this is going to, in other words, the partial with respect to theta of kq over r is 0. There's no theta dependence there. The partial with respect to phi of kq over r is also 0. So these two terms don't have any contribution here. And what I get is minus kq partial with respect to r of 1 over r in the r hat direction. Well, let's take the partial with respect to r. The kq came out because it's k and q are constant. So I have minus kq. Now, the derivative with respect to r is going to be minus r to the minus 2, and in the r hat direction. So there you go. Very simple example, but I was able to reproduce the electric field from a point charge by taking the gradient of the voltage, of the potential. And so there's some more complicated examples. Electric field of a ring of charge, 718. Maybe you can see that you've got cylindrical symmetry there. But it only asks you to find the field along the axis, which means that you only need to worry about the z component of it. And so that's actually pretty straightforward. And so this kind of summarizes the theoretical content of the chapter, and from here on out it's just applying this to work problems. So the next video will be chapter 8, dealing with capacitance.